Next is performance parameters. So, there are certain parameters based on which we measure the performance of any regulator, whether it is a switching or a linear. So, the first one is obviously efficiency, which is measured by this formula P out over P in, where P out is total output power total input power. Okay. So, your P in is nothing but P out plus P loss. So, let us say if I do not know P in, but I know the efficiency, I can still calculate the loss. So, I can write this P out over this implies P loss equal to P out into 1 minus 1 over eta. Correct. And when once I know the P loss, I can directly calculate P in simply by adding P loss into P out. So, you do not need to know both in order to calculate the efficiency. You can either measure P in or P out and calculate the efficiency. If I know P in, then my formula will change. So, I can write P out as P in minus P loss over P in, and this will become 1 minus P loss over P in. Now, my P loss will become in this case 1 minus eta into P in, correct. So, in most of the cases the P out is known. So, this is most frequently used formula in order to calculate the efficiency, and that is what we did here actually. So, we know the output power and how much loss based on efficiency we know 90%, and we can directly calculate the input power, and that is what we did in order to calculate P in here. So, efficiency curve in most of the cases is measured with load current. So, depending upon the type of regulator you are using, in case of switching regulator, it mostly looks like this. At light load, it will peak in some mid range, and as you keep increasing the load current, your I square R losses will increase. So, efficiency will keep dropping. So, you get maximum efficiency here at this load, and at light load and higher load it may reduce. So, it will peak in certain range of the load current, and most of the cases we target this max efficiency of 90% or above in switching regulator. In linear regulator, your efficiency curve may be different. Most of the cases it may be shifted down based on your dropout voltage, or it may go even higher than linear regulator if dropout voltage is very less. So, let us say I want to generate 1.8 volt and my input is 1.85. So, 50 millivolt is the drop. So, 1.8 divided by 1.85, it will give me 97.3%, which is very high. it's almost impossible to achieve with switching regulator in that case. Then second one is your load regulation. So, load regulation is measured as change in output voltage with respect to change in load current. So, if I say delta V out is the change in output voltage and delta I load is the change in load current. So, and I load is, I know it is nothing but output current. So, and this is nothing but output resistance in a small signal. So, you can say it is volt per amp or ohms. In most of the cases we say like because it is order of millivolt roughly. So, we say this millivolt per amp or something, that is how we define this load regulation. So, we do not want my output to I mean to change when load is changing. So, ideally I want R out to be 0, and that is why we say like ideal supply has a 0 output impedance. That is what it means, because it will give you a constant voltage across any load current. So, this is your ideal, this is your V out, but in reality it will not be like this, it may be something like this. And if let us say, okay, let me change the color so that it looks better. Okay. So, if this is delta V out and let us say this is going from 0 to I load max, I load max, then load regulation is delta V out over I load max. So, if let us say I load max is 1 amp and this maximum delta V out or deviation we see let us say 10 millivolt. So, we can say 10 millivolt per amp is my load regulation. And which is nothing but we will say that your output impedance is 10 milliohm, you can say that also. So, third one is line regulation. So, line is nothing but input voltage V in. So, we define it delta V out over delta V in, which means change in output voltage with respect to change in input voltage. Okay. So, this now becomes V in and this becomes V out. So, this is my ideal. But in practical it will not be like this, it may this is much. change the color. So it may do this or it may do like this. So it may be in both the directions, positive or negative, we don't know, it all depends on design. So if this is your delta V out, and let us say my voltage here is, I am going from 2.5 volt to 3.5 volt. So which is 1 volt actually. The simplicity I wanted to keep the difference 1 volt. So line regulation is nothing but delta V out over 1 volt, and if this is, let us say, again I can say 10 millivolt, then I can say 10 millivolt per volt. Okay, just like in this case, if I assume this is 10 millivolt and this is 1 amp, then this becomes 10 millivolt per amp. So that's it, line regulation. So okay, so next performance parameter is line transient. So if this is my input supply voltage, which is not fixed but changing. So let us say this is your V in, and it is going from 1.5 volt to 1.8 volt. Now let us say my output is regulated at 1.2 volt constant. So this is my V out, which is 1.2 volt. So this is your regulator. I will just take an example of this linear regulator, and this is my load. Or let me draw current here. This is my I load, and this is your V in. This is your V ref, which is, let us say, 1.2 volt. So V out is also 1.2 volt. So what would happen actually when V in changes? So this pass transistor, which is MP, it will create a VGS difference, because this gate voltage cannot change instantaneously. So the current in the output will increase, and this will try to shoot, and then since it is a feedback system, the feedback will try to recover, and the recovery time will be depending on your bandwidth, and since it has a finite bandwidth, so this gate voltage cannot instantaneously change. So depending upon how fast your loop is, this overshoot will be determined, and then it will come back, and then again we will start regulating at 1.2 volt. Now same thing will happen when it goes from 1.8 to 1.5 volt. Now we are reducing, so output voltage has to reduce. So this will go low and then try to recover. Okay. So you will see a transient here, undershoot and overshoot. So if I call it this, let us say this is delta V UV under voltage, and this is, let me move this, (1.2 volt). So, I will call this guy delta V OV, over voltage. So, most of the systems have specification for your regulated output voltage. So, I mean most of the system can afford plus minus 10% variation, but then that 10% includes everything, your error, your line transient, load transient. So, this spec for usually transient it is defined within 5% or less, so that you keep the rest 5% margin for other errors. And when I say this 5% spec for this delta VOV and delta UE should be less than 5% of V out. Okay. So, which means for 1.2 volt, so this is your, we call it undershoot, and this is your overshoot. So, for 1.2 volt, delta VOV and delta VUE should be less than 60 millivolt. Okay. So, which means your output should not be more than 1.26 volt and should not go below 1.14 volt. So, next one is your load transient. Yeah, anyway. So, then other than this undershoot overshoot, we have one more transient spec called settling time. Which means T settling, this is defined as time after transient is applied when V out settles within 1%, okay, of the desired voltage. So, which means if we can roughly say this is your T set. Okay. So, next one is your load transient. So, it is similar to your line transient, the difference is instead of changing V in, we change load here. So, if this is my I load, so let us say this is going from 0 to 1 amp. Okay. So, what would happen if this is my V out, again let us say 1.2 volt, then when you apply the load current, what would happen? Your output is regulated and there is no load current, or you can say very small load current, maybe order of milliamp or microamp. So, all of a sudden when you apply the load current, this MOSFET MP has to basically increase the current in order to hold the output voltage, but due to limited bandwidth, again the same problem will happen, that current cannot change suddenly, and so which means all the load current for a very short duration or the duration for which your loop recovers, all the current will be supplied by your capacitor, and capacitor will start discharging and then recover back again, and same thing will happen when you release the load. When you release the load means all the MOSFET current will get dumped into the capacitor and it will cause overshoot. So, again the undershoot overshoot is similar to what we have, the delta VOV and delta UV, and T settling is the T set is the settling time here. So, this undershoot overshoot obviously in both the cases will depend on the bandwidth and value of the output capacitor you put. So, if I want to reduce, let us say once my bandwidth is set, I want to further reduce, then only way is to increase the output cap. Another thing we need to remember in both line transient and load transient is this undershoot overshoot will also depend on how fast you change the input or load current. So, let us say I am changing this 1.5 volt to 1.5 volt to 1.8 volt in let us say 10 nanosecond. So, that is a very fast change. My bandwidth cannot respond, this feedback loop cannot respond that fast. But let us say I make this change in order of 10 microsecond or so, let us say. So, this change is very slow and this feedback will track because it is not very fast, and you will hardly see any undershoot overshoot in the output. So, it all depends how fast you are changing. So, if your change is comparable to your bandwidth or slower than your bandwidth, then this undershoot will be very small, but if you make that change very fast, which is much faster than your bandwidth, then this undershoot overshoot will be significant, and then in that case it can only be reduced by increasing the capacitor or increasing the bandwidth. But once you have designed your regulator, it is fixed, there is no way but only to increase the capacitor. Okay. Power supply, ejection ratio. So, this is defined as PSRR equal to change in output voltage delta V out over delta V in. So, what was this previously we defined delta V out over delta V in? Line regulation, but that was for DC. Now, if you define it for AC, then it becomes PSRR. You can write in dB 20 log 10 . Okay. So, one example could be, so let us say take the case of a charger, okay, battery charger. So, what do you have? You have 220 volt AC, then it goes to your adapter, correct, then it goes to your DC-DC converter. So, this guy will have ripple, okay. So, this will be rectified voltage, you have a capacitor, then it will have some ripple in the output, and DC-DC then output is switching converter, again it will have some. So, this is your 5 volt which goes to your USB, then it will also have some ripple. So, if this is 50 hertz, this should be 100 hertz. Okay, but this DC-DC is switching at much higher frequency, maybe 1 megahertz or 500 kilohertz. So, it will have a higher frequency ripple. It may have some portion of this 100 hertz also component, but it is a very low frequency, your loop can track. But when you have a high frequency ripple, your loop will not respond to that, and that will start appearing at your output. Okay. So, anything you are, you looked at the line transient, you make a sudden change in the line, what happens? Your loop cannot respond that fast, and you will see dip or undershoot or overshoot in the output. It is only because your loop has limited bandwidth. So, same thing applies here also. The only difference is, instead of a step, now you have a more like a sinusoid ripple, but the concept remains same. If this frequency component is so high that your loop cannot track, then that component will appear in the output of your regulator. So, now this is your regulator, which takes 5 volt and gives you, let us say, 1.2 volt. Okay. Output, this is your V out, this is your V in, and this is not clean, this has some ripple, which could be anything like maybe 10 millivolt, 20 millivolt, depending upon the converter specifications and the value of the capacitor which is put here. Okay. So, what all can be done to improve this PSRR? Yeah, that may be the one case, but that is not always true. It depends how you have designed your, when we will come to the designing the regulator, you will know that it is not that output cap will improve the. So, it depends what is your dominant pole, whether the dominant pole is your inside the regulator or the output. If your dominant pole is inside the regulator, then your bandwidth is limited by the pole, not with the capacitor. So, increasing the cap may not help here, okay, until unless you make this dominant. If you make the output pole dominant, then obviously it will always help, okay, because you will get a direct filtering from input to output, and so it will behave like a low pass filter. So, making the low pass filter bandwidth lower and lower will reject more higher frequencies, and that will help. But if you are relying on the bandwidth, then larger the bandwidth is, so there are two ways to suppress the ripple. One is you just filter it out through the capacitor, which is only possible if you make output pole dominant. Other way, you make your, it is a feedback system. So, if there is any change in the output, your feedback will try to correct it. So, what it will do actually, when it sees any ripple in the output, it will try to change the gate voltage of the FET in such a way that nothing appears across the VJs. Okay, so think about this. You have this is your R load, and this is your output cap V out, this is your V in, which has some ripple, V ref, okay. So, what would happen when any change appears here at the V out? If I call it V gate, unless your V gate changes, if let us say V in is changing, unless your V gate changes, the whole thing will appear in the output. In fact, let us say if you make the V gate constant, what is appearing at the, so the voltage which is appearing at the gate is your VGS, gate to source voltage, and if you assume the small signal of V gate is 0, because it is not changing, your bandwidth is very slow, it is not changing. So, everything the AC, all AC component which is appearing at the V in will get amplified by the GM of this and appear at the output. So whatever the R out, so GM R out is the gain actually. So this is looking like your, what type of amplifier will this be? Why common source? Common gate, because input is at the source, input is at the gate and your source is grounded, then it's a common source, because common node is gate here, because gate is not changing. So it will behave like a common gate amplifier and everything will appear here, and it will make it even worse because this is acting as an amplifier. So what do you want? Which means now if I increase the bandwidth in such a way that, let us say this guy is 100 kilohertz, my bandwidth is 1 megahertz or so. So which means 100 kilohertz can be easily tracked. If this is any change in the output, what would happen? Your output will be fed back here, and same time it will try to change the gate voltage. So let us say this changes by a plus minus 10 millivolt or so. So it will try to change the gate voltage by plus minus 10 millivolts. So AC variation across your gate to source remains 0. So if they are in phase and they have a same amplitude, they will cancel out. So and that's what the feedback does actually, but you are limited by the bandwidth. Okay. So you can track up to the bandwidth of your amplifier. So if your signal frequency or the AC variation at V in is more than the bandwidth of this amplifier, then it cannot track. In that case, some portion will appear at the gate, but will be very smaller, and which means it will keep on amplifying and amplifying as you keep increasing the signal frequency, and more will appear at the output. So it will look like a high pass filter. I mean your system will look like a low pass filter, but if you look at a PSRR, it will look like a high pass filter, because at lower frequency you will get a rejection, but at higher frequency you will not get the rejection. But then after that, when this guy kicks in, this capacitor, then you have an additional pole, then it will try to attenuate the signal. So it will go high, and then so it will more look like a band pass kind of a behavior. But if you make this output dominant, then it will look like a low pass filter perfect, which is the desired case, but it is not easy when you design the regulator to make the output pole as dominant, because most of the case these value of these caps are very small. So there is no way, unless you put order of microfarads also, and we prefer these on chip regulators not to put any external cap, and on chip we can mostly we can put tens of picofarad. So you can never make this dominant pole, that is a problem. Okay. So there are some techniques where you cancel this, you inject this noise at the gate, and you can try to cancel and improve the PSRR. We will talk about that when we discuss the design of your linear regulator. And this is very important, and that is one of the reasons sometimes at the output you need a linear regulator, I mean output of switching regulator, because switching regulator are noisy, they will have ripple in the output, and you want to filter that. So if you have a noise sensitive application, let us say RF or analog, and it is driving very high current, then you put a DC-DC converter followed by this linear regulator, which we call sub regulator, and if you keep the dropout very low, then you won't lose too much in the efficiency. And if your regulator has a very good bandwidth, this linear regulator, then you can filter out those ripple and output will be much cleaner. So instead of 10 millivolt, you might see less than 1 millivolt ripple in the output, which will be sufficient to supply to your noise sensitive application. It could be RF, analog or any other application.